Hello and welcome to this IChemE Global Awards 2021 webinar. My name is Matt Stalker and I'm your host for today's presentation. The IChemE Global Awards celebrate chemical, process and biochemical engineering excellence and are widely considered as the world's most prestigious chemical engineering awards. Today we'll be revealing the winner of the IChemE Young Researcher Award, sponsored by the Chemical Engineer. This award recognises the chemical engineer under 30 years of age who best demonstrates the impact of their chemical engineering research to address important technical, economic, environmental or social issues. Our awards judging panel has been hard at work in recent weeks to review and rank all of the candidates, and here are our finalists. We have Thomas Meachin from Stream Sensing, Amani Al-Gamadi from Saudi Aramco, Ko Kok Young from the National University of Singapore, Zhao Chen, also from the National University of Singapore, Neil Robinson from the University of Western Australia, and finally, winner of the IChemE Malaysia Young Researcher Award, Bin Sheng Hao. All our finalists have been invited to join us today to tell us more about their work and to answer your questions. You can get in touch throughout today's webinar using the GoToWebinar questions box on screen. So let's get started with our first finalist. Please welcome Tom Meachin.
Can everyone see my screen?
Yes, we can, and we can hear you loud and clear, Tom.
Good. All right, okay. So hello, everybody. I'm Dr. Thomas Meachin. I'm the Senior Technology Officer at Stream Sensing, and extremely proud to be a finalist at the IChemE Global Awards. So I'm going to present to you some of my work, which focuses upon characterizing complex fluids using electrical resistance sensing. So just a bit of background about myself. So I did a Master's in Chemical Engineering at the University of Birmingham. That was completed in 2015. Obviously enjoyed it so much that I went on to do an engineering doctorate with the university, and that was also an industrial doctorate based in a company called Industrial Tomography Systems. So the research I worked on led to the spin out of the company Stream Sensing. Since 2020, I've been the Senior Technology Officer. So just a bit of background about my research. So the digital world has obviously already breached a huge number of sectors, including finance, healthcare, media, and there's an ever increasing demand to apply these digital processes to manufacturing. I'm sure you've all heard of Industry 4.0. So that's an integrated approach which aims to develop production systems which are interconnected, communicated, and take process data to inform process decisions. There's still a challenge within this to develop new sensing, real-time sensing diagnostic methods which can be used to then inform these process decisions. So my research is basically focused on the development of these new technologies using a technique called electrical resistance sensing, or also electrical tomography. So it's focused on three key areas. So the first is the characterization of the product microstructure, or rheology. So this is a patented technology which has led to the founding of Stream Sensing, which has then gone on to receive venture capital investment to grow and be commercialized. Also developed a novel fingerprinting methodology to fingerprint different formulations. So that's also patented, and that's been applied in a number of operations. So been looking at the product recovery and cleaning time and cleaning cycles, different compositions and rheology of surfactant electrolyte formulations, and gas liquid mixing flow regimes. So also looking at the characterization of non-Newtonian solid liquid mixtures in non-nuclear densitometry. For the sake of brevity, I'm going to focus on one application, so looking at rheology. And rheology impacts every aspect of our daily lives, from the texture of the food to making sure that when you brush your teeth, you don't end up with toothpaste on your shoes. It's also critical in chemical and physical process and governing your process efficiency and also the final product quality. So typically what would happen is you would take a sample of your product at the end of a process, take it to the lab, analyze it, and then if it doesn't meet the quality control standards, then potentially a batch would have to be scrapped or completely reworked. And what this does is obviously creates large volumes of waste and large amounts of energy consumption. Using an inline approach and measuring the rheology in a pipe overcomes this, and as well as it has a number of other advantages. So it allows you to unlock production capacity, as it's a basis for real-time product release, improve quality control responsiveness, and also help enhance process design and understanding. So the technology which it's based on, and a lot of my work is based on, is called electrical resistance technology, or it can be tomography. And essentially the best way to think of that is it is a CT scan, but rather than using X-rays, you're using an electric field. So as well as rheology, you can start to get information like mixing, aeration, things like that. So if you look at the picture of the sensor in the bottom left, you can start to get images like at the bottom, which show the distribution of materials within your process. And the way we use it for rheology is that the laminar velocity profile in a pipe is heavily influenced by the rheology of the material. And we measure the rheology by tracing the motion of the fluid across multiple planes of imaging. So obviously we know the electrodes are fixed. We know how long it takes to get from one plane to the other. So then we can start to extract the laminar velocity profile. And with this technology, we couple the velocity profile with the differential pressure measurement, and that can be used to extract viscosity at key quality control set points, and also output conventional rheometry plots such as sort of shear stress, shear rate, which you get from a rheometer. As I mentioned before, you can also get mixing behavior at the same time, which makes it a powerful characterization tool. So once you've got the velocity profile and the differential pressure measurement, there's sort of a number of approaches we can take to get the rheology. We can differentiate the velocity profile. A favorite approach is a parametric fit into rheological models, so say a power law fluid. But often in industrial fluids, they're a lot more complex than that. So you have one velocity profile trying to fit to say 5-6 parameters, and that makes it slightly ill-conditioned. So there's also another approach which we developed using machine learning and neural network approaches to extract rheology. So how does the system perform? So the first thing we did was validate the velocity profiles we get from the technology, and this was done using particle image velocimetry, which is a laser-based technique which is of high resolution. However, obviously, if you're using lasers, it's not ideal in an industrial setting, and it's limited to transparent fluids. But what it was able to do is to provide us confidence that the velocity profiles which we're measuring were accurate, as we got a high correlation coefficient of 0.99. I guess the ultimate test is to validate the technology against an offline rheometer. So within a flow loop, we had a 1-inch flow loop and a 1-inch sensor. And basically, we picked fluids such as glycerol, xanthan gum, carbopol, which have a limited time shear dependency. So if you're taking a measurement in a pipe, it should be relatively similar to what you're taking offline. And this was used to basically to validate the technology against a rheometer. And what we found is the approach that I developed was able to accurately monitor inline rheology with an accuracy of 98%, which is really positive. This is just sort of a separate experiment just to show how the two can be linked. So, and this was done in a similar flow loop, but it was recirculating. So this was started off with a very low concentration xanthan gum solution. Added to that, we added a really high concentration of xanthine gum, so it was mixing over a period of time. And what we were able to monitor was the evolution of rheology over time by the rheology measurements, and also measure the distribution of the electrical properties within the sensor, so we can start to see when the process is mixed and when the process isn't mixed. So you can do things like coefficient of variance measurements at the same time. So it then becomes a really powerful characterization tool. So this was another approach we used. So this was essentially, the aim of this was to replicate a quality control process for rheology. So this was done at a manufacturer of home and personal care products using industrial fluids, and what we wanted to do is people tend to measure viscosity at key control set points. So we picked a viscosity at a certain shear rate, and then to see if we were able to match this using our system. And what we were able to do was gain an accuracy of sort of plus or minus 5%, which is great. And then this can be then used for unlocking process capacity, optimizing batch time release, and then also automating quality control principles. So just a brief summary of my work. So developed basically new inline sensing and diagnostic tools to characterize complex industrial fluids, focused on inline rheology, which obviously has a number of measurement advantages, which I talked about. I also developed two more techniques, which I haven't had a chance to really touch on, looking at fingerprinting of fluids and characterizing non-Newtonian fluids and for non-nuclear density measurements. So if anyone wants to talk to me about that, it'd be great to after. But yeah, just before I finish, just like to thank everyone at University of Birmingham who's helped me through my research, everyone at ITS, and everyone at Stream Sensing. So yeah, thank you very much for listening.
Okay, thank you very much, Tom. We will pause for questions. So if you have any questions for Tom, now is the time to type it into the questions box. Okay, we don't appear to have any questions, Tom, so thank you very much. We'll move on to our next presentation. Please welcome Amani Al-Ghamadi.
Hello, good morning, everyone. Can you see my screen?
Yes, we can, yes.
All right, so my name is Amani Al-Ghamadi. I'm a research scientist. I work with IChemE Advanced Research Center in Saudi Aramco, in particular Reservoir Engineering Technology Division. I have been with Saudi Aramco for 3 years, and before that I finished my master's degree in physical chemistry from King Abdulaziz University in Saudi Arabia. And my research journey started by looking into the catalysis processes that takes place in hydrogen fuel cell. In particular, we looked into the opportunity of producing hydrogen from cycloalkanes and methyl cycloalkanes when they are converted into the corresponding alkanes in a process that requires a catalyst. So this process produces hydrogen that can be used as a source of energy. As we all know, hydrogen can be an excellent source to produce energy. However, the storage of hydrogen is problematic. So the promising solution in here is to store it in the bonds of methyl cycloalkanes and cycloalkanes. However, as we all know, this reaction is endothermic. and requires a catalyst. The best catalyst for this reaction is platinum. However, it's quite expensive, but it's the best to lead to the main reaction that produces hydrogen and prevent the side reaction that leads to the cracking of the carbon-carbon bond. Looking into different elements that can replace platinum, nickel have emerged as a potential replacement, along with other elements, also as metal alloys in the form of nickel, zinc. So the contribution, our contribution to this was to look into the intrinsic difference between platinum and nickel in the full dehydrogenation cycle when it's converted from methyl cyclohexane, for example, into toluene. We looked into the cracking of the carbon-hydrogen bond over those metallic surfaces, flat surfaces actually, 100. Using DFT calculations. We provided different insights into the full thermodynamic cycles and the energy required for each step. And we saw that nickel provides promising efficiency for this process with a certain degree of energy efficiency. We also looked into the chemical insights that could take place at those flat surfaces. In particular, if we look into the methyl substituents in methyl cyclohexane, we can see that the cracking of the carbon-hydrogen bond from the methyl group is exothermic process that leads to the stability of this species of and leads to the stacking of the parent molecule into the surface and enhanced stability due to the chemical changes that takes place at the methyl substituents, leading to the transformation from sp3 hybridization into sp2 hybridization, which provides extra stability to the parent molecule at the interface. We saw that this can be extended to alkyl parent molecules with different alkyl substituents, as well as long branches of alkyl substituents such as xylene and mesethylene and ethyl benzene. And this actually provides in-depth atomic understanding of the essential role of hydrogen co-feeding to produce alkyl aromatics in the industrial applications. The second part of my research, which was taking place during my work in Saudi Aramco, is in the area of enhanced oil recovery. And in this area, we looked into the opportunity of smart water flooding to enhance the oil recovery in tertiary processes. So it's more or less better than other enhanced oil recovery processes like chemical processes or thermal processes. It's less energy intensive and provide less environmental impact. It requires the changing of the chemical composition of the water, either by reducing the salinity or altering the concentration of divalent cations, or increasing the concentration of different anions. However, this process is not quite understood in terms of the mechanisms that leads to the success of those processes, and further fundamental understanding is required, especially at the atomic scale and the nano and the micro scale. So our contribution in this was into the understanding of the physiochemical interactions that takes place at the interfaces of this very complex system of oil, water, and rock surfaces, especially carbonates, since most of the reservoirs in Saudi are carbonates. So we looked into the electrokinetic interactions that takes place at the oil brine interface as well as the water brine interface. We found that the electrical potential at those two interfaces differ drastically when you change the composition of the water, either when you reduce it, as in the case of smart water, or when you choose certain ions like sodium sulfate water. We found that at the calcite water interface, the potential reduces in the case of smart water, which is very promising in our case. As you can see in this slide, in case if you have high salinity water as in seawater, this would lead to the different potentials at the oil-water interface and the calcite-water interface, which should lead to an oil-wet system, unfavorable for enhanced oil recovery. And when you change the water into smart water, this would lead to similar potentials at the interfaces, which leads to water-wet system, and this is evident in the contact angles that we observe also in our labs. That's it for me. Thank you all for your kind listening. I'll be happy to take any questions.
Okay, thank you very much. We will pause for questions then. So if you'd like to get in touch, please do so via the questions box now. Okay, we don't appear to have any questions, so thank you. We're going to move on to our third presentation of the day. It's the first of two finalists from the National University of Singapore. Please welcome Ko Kok Yen.
Are you having a problem, Ko Kok Yen?
Am I sharing the screen now?
No, not yet.
Not yet.
There we go. Perfect.
All right. Okay. Hello, everyone. So my name is Ko Kok Yuan. So so the outline of this presentation, including my backgrounds, so some research experience. Then today I'm going to share my PhD research summary. So I'm a Malaysian. So I just graduated in NUS, National University of Singapore. So currently I work as a research engineer in NUS Environmental Research Institute. So so this is my research experience. Currently I'm working in the algae removal project. So during my PhD study, the main focus is the development of a series of latanium-based material for the nutrient phosphorus removal. Other than that, I also involved in other projects such as electrochemical disinfection system and also microplastic project. So now I'm going to share my PhD research. So the topic is the latanium-based material for nutrients phosphorus removal from aqueous solution. So as we know, phosphorus is a common element in the environment. So it mainly exists as a phosphate, which is a nutrient for the organisms. However, it can cause a drawback to the environment if it is excessively exists in the surface water. It can cause the algae bloom and subsequently resulting in eutrophication. So my objective is to remove this phosphate from the water, and it has been found that a material, a rare earth material called latanium, which has a strong affinity towards phosphate. So my PhD research focusing in developing the latanium particle for the adsorption. Other than that, I incorporated latanium element into the hydrogel beads and membrane for adsorption and filtration processes. So this is the first part of my PhD research. So it's using latanium carbonate particle. So firstly, the particle was optimized using Volkswagen design model in order to obtain the best synthetic conditions for the synthesis of latanium carbonate with the highest adsorption capacity. So we can see that at the higher concentration of urea, lower temperature and time will resulted with the highest adsorption capacity. So as shown that this material has good performance for the phosphate removal across the pH range, and then it can shows a consistent performance even in a complex wastewater. So other than that, it also can be regenerated and can be reused for the subsequent adsorption process. So the next step is to incorporate LA latanium into the chitosan hydrogel beads. So by doing that, we are able to recollect the hydrogel beads easily from the water for the subsequent reuse. So the hydrogel beads was being optimized by varying the LA concentration and also the cross-linker degree. So it shows that the optimized hydrogel beads with the smaller size, it can achieve a better kinetics, which is comparable to the particles in the previous stage. Other than that, because it has been formed into a bead shape, so it can be used in a column filtration process. So next is incorporate the LA into a PAN membrane. So by doing this, it's also to achieve the similar purpose by make the recorrection process easier, and also this membrane can be applied in the dead-end filtration process. So it shows that the incorporation of latanium, it reduced the porosity and the pure water flux. So we can see that in the filtration process, it can remove pretty well the phosphate, and also it can be reused and also used in the reservoir water. So by introduce the LA into the membrane, so it introduced the adsorptive properties, and at the same time, you are able to remove other pollutants such as organic components. So next, I optimize the incorporation methods in the incorporating of LA into the PES membrane. So by doing the comparison, we are able to obtain the best methods for the incorporation of LA. So we see that the different methods resulted in different LA species on the membrane. So overall, by studying their performance, so we can say that the in situ method resulted in a membrane with the better performance in both batch adsorption and membrane filtration process. Other than that, this membrane is able to show a comparable phosphate removal when we compare with it with the nanofiltration membrane. Thank you for your listening.
Okay, thank you very much. So once again, we'll take a short pause for Q&A. So if you have a question, now is the time to get in touch. Okay, once again, we don't appear to have any questions, so thank you. We will move on to our next presentation. Please welcome Neil Robinson.
Okay, thank you very much. Thank you for the introduction. My name is Neil and I'm a postdoctoral research associate at the University of Western Australia, which is in Perth. Prior to this, I completed my PhD at the University of Cambridge in the UK. And prior to that, I was an undergraduate chemist at the University of Cardiff, UK. Today, I just want to give you a short overview of some of my research, which focuses on the application of magnetic resonance techniques to characterize porous materials of interest to the chemical engineering community. So porous media are prevalent across a variety of areas in chemical engineering. My research focuses on the design, synthesis, and characterization of materials for energy, environment, and societal issues. So in a non-exhaustive list of porous materials for these sorts of applications is provided here and ranges from bespoke, well characterized and well-defined systems such as zeolites and zeolites for gas separation and storage, and porous systems for heterogeneous catalysis, across to really more heterogeneous systems, including cements and concretes, and also naturally forming systems that we might be interested in for geosequestration. So the primary workhorse of my research is magnetic resonance, and I don't want to go into a huge amount of theory, but in essence, and by magnetic resonance, I mean nuclear magnetic resonance in this case, typically abbreviated to NMR. NMR leverages the inherent magnetism of many atomic nuclei and the fact that we can utilize the application of magnetic fields and radio frequency pulses to control that magnetism in order to generate some sort of signal. And so the signal that we typically get out of an NMR experiment is an oscillating signal. An example is shown here, and you can see it oscillates and decays in time. This signal form characterizes the system under investigation really quite well. So in a chemical environment, in a chemistry department, or a chemistry research lab, or a biochemistry research lab, the interpretation of this kind of data is typically done by looking at the frequency data, so Fourier transformation to take this data into a frequency spectra. And it's well known that the frequency behavior of NMR data is sensitive to the electronic environment of the molecules or the solids that you are analyzing. And so it's a very well-established probe of molecular structure. In the case of understanding fluid behavior, and by fluid I mean gas or liquid or a combination, fluid behavior in porous materials, however, this process is usually not quite as useful. And I've tried to demonstrate this on the bottom left here by showing you some NMR spectra taken from ethanol, both in the liquid bulk phase and also when it's confined within some porous silica. And you can immediately see there's a drastic loss of resolution within the porous system. And so actually NMR frequency spectra is not quite as useful as you might think it could be when characterizing fluid behavior within porous systems. And so what I tend to do is look at this data a little bit differently and instead look at the rate of decay of the signal rather than the rates of oscillation. And this is called the relaxation behavior. So relaxation is characterized by time constants. These are called T1 and T2. There's two different time constants. And a typical thing we might do is look at a distribution of these time constants. This example data is from my colleague Ming Li here and shows the relaxation behavior of methane confined within certain rock structures. And importantly, relaxation data is very sensitive to molecular dynamics. So while frequency data is sensitive to structure, relaxation is sensitive to dynamics. And this is a particularly useful probe of porous materials and of fluid behavior within porous materials. And it's this behavior that I leverage in my research. So there's an awful lot of relaxation theory, which I won't go into at all today. But the important takeaway messages before I show you any of the results of my work are that relaxation processes can be measured very easily using well-defined NMR experiments. And for porous systems where we have a probe fluid within the system, the observed relaxation behavior, so what we measure, is actually an interesting function of both the material structure, which I've described in this expression here through the surface to volume ratio, and also the interfacial chemistry. And so we can leverage the measurement of this relaxation phenomena in order to gain possibly both sets of information. I think this is really fascinating bit of chemical engineering science. What I'm going to show you today is just a quick example of using relaxation data to look at both of those phenomena. So how can we use relaxation data to test out essentially material structure, and then how can we also look at interfacial processes? Just quickly before I do that, I'm going to mention that the NMR hardware that we use is not the typical NMR hardware you might have experienced in your, for example, undergraduate degree. So on the top left here is a typical NMR spectrometer. It's a high field superconducting system. It's full of cryogenic liquids and it has a very high magnetic field. For chemical engineering type analyses, what we tend to use actually are low field benchtop systems, as shown in the middle here. And so a key characteristic of these is that the magnetic field, a very important component of the NMR experiment, is instead generated by a series of permanent magnets rather than a superconducting system. And this means that the magnetic field is slightly lower, and so we tend to refer to experiments performed using this hardware as low field NMR. So low field benchtop NMR actually has quite a few significant advantages over its high field cousins. So because of the reduction in size and also mass, low field NMR systems tend to be quite portable. So on the top right here, I'm showing an example of researchers from the group that I currently work in at the University of Western Australia, actually taking a portable NMR system out into the field, not to do any research to do with porous materials in this case, but to look at oil and water systems. Because they use permanent magnets rather than cryogenic liquids, there's no cryogens to deal with, so you don't have the safety or cost concerns of constantly replenishing liquid nitrogen and liquid helium, which are present within the superconducting system. And so that has, as I said, a large reduction in cost and safety. It also means that these low field benchtop systems are pretty much maintenance free. And that's key in terms of their application in, for example, high throughput screening technology, where you might not have an expert using them. So their use in almost push button applications is much more prevalent for the benchtop NMR systems. I've added another bullet point just down on the bottom right hand side, which I'm not going to go into any detail, but actually if we do relaxation measurements at low magnetic field, we can actually measure relaxation phenomena more accurately than high field, which is obviously an added bonus. So I'm going to show you just two examples of my recent research. The first is using magnetic resonance to probe material characteristics, and the example I'm going to show you is a really quite special piece of work I was lucky to be involved in last year, and that's using relaxation to characterize pore-to-pore exchange in a hierarchical catalyst structure. So both examples I'm going to show you are to do with heterogeneous catalysis. This particular example is a characterization of what's called a spatially orthogonal catalyst, which is designed for chemical cascade reactions. So chemical cascade reactions, or one part of chemical cascade reactions, I should say. So the aim here is to develop and utilize a bespoke porous material which catalyzes an initial reaction and then can also catalyze a second reaction, so that there are two sequential reactions occurring within the same material. This material and this catalyst can do that by having spatially segregated active sites within pores of different size. So this material is based on templated mesoporous silica, but it also has integrated macropores, and the macropores and mesopores will functionalize differently so that one pore size will catalyze the first reaction and one pore size will catalyze the second reaction. Critical to the validation of this material, however, was knowledge of the route in which fluids take from the external bulk into the material? Do they go bulk macropore mesopore, or do they go bulk mesopore macropore? And so I last year utilized magnetic resonance in the form of quite a complex 2D correlation set of experiments to actually probe this. So this is actually the only known experimental route to this behavior. And so what we're showing here are what's called 2D correlation plots, where we've measured this time constant T2 twice, and it's separated by mixing time. Now, experiments done with short mixing times probe diffusive exchange over short length scales, while experiments performed with long mixing times probe diffusive exchange over large length scales. And so by varying the mixing time, we were able to probe diffusive exchange throughout this structure across a variety of length scales. And we were able to show that there was clear connectivity between the mesopores and the macropores. And more importantly, we were able to show that there was clearly a well-defined diffusive pathway that went from the bulk to the macropores to the mesopores. And so this knowledge informed the location upon which the different active sites needed to be placed during material synthesis. The second example I'm going to show you is to do with absorption. So looking at the surface affinity of liquids within catalyst materials is critical in, for example, solvated green chemical processes, where you don't want your solvent to outcompete with your reagent for the surface. So the ability to rapidly and non-invasively characterize the surface affinities of liquids within different porous catalyst materials is critical. And so in this piece of work, I demonstrated the use of a slightly different NMR measurement, what's called the T1, T2 correlation measurement, where we simultaneously measured these time constants T1 and T2. I was actually able to provide rapid access to surface affinity information. And we do this through this dimensionless ratio called the T1, T2 ratio, which up until this work was basically theorized to be related to the surface affinity, but there wasn't a huge amount of evidence to back that up. And so in this work, we looked at a series of C1 to C4 primary alcohols, so methanol through to butanol, interacting with a model silica surface, and we recorded the T1, T2 ratios, also cyclohexane as a non-interacting reference. And then we compared that with adsorption modeling. So using periodic DFT, we calculated the adsorption energetics at the single molecular level, and then provided a direct comparison between the NMR acquired relaxation surface affinity data and the DFT molecular modeling acquired adsorption energetics. And this is in the bottom right hand data set there. And you can see there's clearly a very strong correlation here. So this really demonstrated the potential of NMR relaxation as a rapid and non-invasive screening tool for looking at surface affinities and competitive displacement interactions. So that was a whistle-stop tour of just some of my work. I'll just end by acknowledging that this is definitely not a one-man show. There's a huge amount of collaboration that's gone into the two pieces of work that I've shown you there. If I had more time, I could tell you about 10 more, but primarily I want to thank my current supervisor, Professor Mike Johns, for the nomination, and my PhD supervisors, Dr. Carmine D'Agostino and Stephen Jenkins, and my other collaborators at the Universities of Cambridge, RMIT, Manchester, UCL, and everyone else that I've worked with over the previous years. So thank you very much for your attention, and I'm very happy to take any questions.
Okay, thank you very much, Neil. We'll pause once again for questions. So if you would like to get in touch, now is the time to do so. Okay, once again, we don't have any questions, so thank you very much, Neil. We will move on. Next up, we're going back to the National University of Singapore, and it's Zhao Chen.
Xiao Chen, are you able to share your screen?
Okay, while we give Zhao a few moments to sort things out at his end, we'll move on to our next presentation. This is a pre-recorded presentation from the winner of the IChemE Malaysia Young Researcher Award, Hao Bing Shen.
Good morning, good afternoon, and good evening, everyone, depending where are you from at the moment. I'm Hao. It's my honor to be selected as one of the finalists in this IChemE Global Award 2021. In the next few minutes, I will walk you through the research area that I was and currently ventured into. Just a little bit of myself. I'm currently serving as a lecturer and researcher in Swinburne University of Technology Sarawak campus. As stated, I have published for more than 60 publications up to date with a H index of 16. I've been promoted as an associate editor of Frontiers in Sustainability in the early 2021. Just a small advertisement, my team has recently called for paper submission for a special collection with a theme of Towards Artificial Intelligence for Chemical Process Synthesis, Design and Optimization. Any interested party, please feel free to contact me or browse through the official Frontiers website for more details. Given to my research excellence, I've been selected as one of the winners of the Young Researcher Award category in IChemE Malaysia 2021. In addition, I managed to secure a total fundings of more than £65,000. I will brief this through later on. You may be curious, what is my research focus? Well, I will need to present this using a timeline chart here. In the first 4 to 5 years of my research, I heavily focus on biomass supply chain management since this is my research area for PhD study. In fact, more than 50% of my work are related to this area. Forgive me that I'm unable to show you all of my works given the short time frame today. Instead, I will walk you through some of my research which I think is worth to be highlighted today. The first work here is related to transportation design that aims to determine the best transportation mode with considerations of physical constraints of the vehicle. In addition to making the model become more efficient, we take one step further. We extract all the solutions that we have conducted and transform it into the graphical tool called SVS diagram shown here. With the aid of this tool, decision makers with minimal mathematical and programming background can now identify which transportation mode to be chosen easily given a known traveling distance and a delivered amount. We are aware that there is a global debate on the sustainability aspect for palm oil industry. Therefore, we believe that transitioning the palm oil industry towards circular model is one of the way out of this issue. This work not only quantitatively evaluates the feasibility of the transition, but also introduces the strategies such as policy refurbishment to overcome the bottleneck that hinders the favorability of the circular model. Speaking of the policy, among so many policies, which policies should be prioritized? My team attempts to answer this research question using Monte Carlo simulation, which considered various uncertainties such as biomass availability, biomass quality, and unit price of the material. Nevertheless, after I graduated, I started to explore more areas outside my comfort zone. I believe that all my skills I learned during my PhD studies are transferable to other fields of research. So why not expand my contribution to a wider area? Based on the statistics shown in the SciVal, my published work covers more than 10 topics where most of them have a citation impact of more than 1. This indicates that the published works have been cited more frequently than expected. Again, I'm unable to capture every single field that I have explored, but I will name a few here today. Green hydrogen economy has been a hot topic in the recent decades. I'm delighted to work with a research team in Kyunghee University to study the optimal hydrogen production technology in Korea. Furthermore, in the Malaysian context, the biogas generated from the palm oil mills serve as a feasible feedstock for hydrogen generation. To assess the feasibility of this pathway, I work with a research team from University of Nottingham to determine the optimal pipeline design, which can be used to transfer biogas to the dedicated hydrogen production plant. Next, lean and green aspect are the important indicators to be considered in process debottlenecking and upscaling. In one of my projects, my team developed a tool called BOTA to assist decision makers in prioritizing the upgrading sequence of further process equipment. Just a side note, this will also present the impact of using different upgrading scheme. For example, if one decided to upgrade all equipment in one go, the payback period required may be longer than that of using a progressive upgrading scheme. More recently, I have started a few projects related to energy planning and resources conservation networks. One of them are focused in determining the heat integrated hydrogen network, which aims to minimize both fresh hydrogen and energy requirement. We propose to solve the problem using P-graph since it is capable of yielding multiple near-optimal solutions simultaneously. With these identifications of alternative solutions, decision makers can then perform a more in-depth comparison and select the one that is most suitable for their specific case. Transforming the findings into reality is always the most important mission for a researcher. Just for sharing, in one of my earlier projects, we are looking to optimize the performance of a real waste oil re-refinery plant in Malaysia. However, given that there is a gigantic amount of process variables to be considered in the plant, the optimization process can be very arduous when using the conventional method. To address this problem, the team have came out with a novel optimization method called Passport, which incorporates the use of PCA to effectively reduce the dimensionality of the problem while ensuring the reliability of the outcome. Based on the pilot testing in the plant, after adopting the improved scheme suggested by the model, the product yield and the overall carbon emissions of the plant have been improved gradually as shown in the slides here. You can find out more in this paper if you are interested. During my industrial attachment in Huachang Gromax, I have asked to determine the optimal oil palm fertilizer formulation. Again, with the aid of P-graph approach, I managed to come up with a few attractive fertilizer formulations for the company. All the findings has been documented in the journal article shown here. Moving on to the grant application, I have secured grants from all three dimensions shown here. In terms of the industrial collaboration, I've led a team in discovering the economic feasibility of building a green hydrogen plant in Kuching, Malaysia. The research served as an important guide for SEDC Energy in identifying the potential gaps prior to the actual deployment of the plant. Last year, we have secured a state fund which aimed to foster research that support green economy and sustainable development in the Sarawak state. In this project, we aim to convert the waste carbon dioxide, the cement waste, and the unwanted fly ash into usable green building material using the absorption and AWL technology. Furthermore, my team also secured few national grants. For example, one of them aimed to explore the feasibility of transitioning the conventional oil and gas industry into circular business model. Generally, we consider two main strategies. The first focusing on the re-refining option for the waste oil, while the later focusing on replacing the fossil feedstock with biomass feedstock. From my understanding, research is meaningless unless the knowledge is transferred. With this, I've actively engaged in numerous community service as shown. For example, I've organized P-graph workshop to the researcher in other institutions. Other than that, I've helped to coordinate a SPC workshop for the medical experts. Furthermore, I am active in exposing my work to a greater audience, either through webinar like the one conducted by IChemE Toxic and through keynote invitation. Last but not least, I'm keen on providing mentorship for the younger generation to become a talented researcher. With my supervision and of course with their own efforts, most of them can perform well in the national research arena. Just to name a few, Ms. Ong and Ms. Ng has been selected as one of the finalists in the CGIG 2020. Before I end my presentation, I would like to share a belief of mine regarding to young researcher. Young is never a constraint, it's a field for us to explore further without fear. That's all for today. Hope you enjoyed the session. Just in case you want to contact me for any matters, here are my contact details. Thank you very much.
Okay, that was a pre-recorded presentation. So we will have one more try with Zhao Chen before we move on. So let's give it one more go. Zhao, are you able to share your screen?
Matt, they don't appear to be with us anymore.
Okay,
I think
in
they've
that
logged
case,
off the call.
we will move on. Thank you everybody for joining us. So we'll move on to finding out who our winner is. So let's start with our highly commended entries. And they are Zhao Chen and Neil Robinson. So well done to both of you. But now it's time to announce the award winner. Ladies and gentlemen, the winner of the IChemE Young Researcher Award, sponsored by the chemical engineer, is Hao Bing Shen. So it was the presentation we've just seen, and I know that Hao is with us on the call. So Hao, if you are able to unmute your mic and perhaps share your camera, tell us, how does it feel to be an IChemE Award winner?
Wow. Can you hear me? It's my pleasure to be getting this IChemE Global Awards. To be honest, it's out of my expectations. I didn't really ready for this winning speech, but yeah, it's a recognition. I'm really happy, and it's my honor to receive this award. Thank you very much.
Well, thank you and congratulations again. And thank you to everybody for being with us today, especially all of our presenters. That wraps up today's webinar. So thank you for joining us and goodbye.